So in section 4.1, we're going to be talking about some terminology. And we first want to talk about an experiment. And an experiment could be anything that we're doing, tossing a coin, asking people about a survey, how many hours they sleep, just so kind of what we're trying to get some information about here. So we're going to do this example by talking about a single die. So that's going to be our experiment, where we toss a single die here. And there are some outcomes. So one specific outcome could be that you roll the number 3. So there are many outcomes, but one of them is going to be that we could actually roll a 3 here. A sample space is going to be a collection of all the outcomes, so everything that's possible that could happen. So with a single die, 6-sided, we could get all the integers from 1 to 6. And we're going to denote this as a set with the squiggly brackets. And so S is going to be the sample size. So it's a set, a group of items that we have. An event could be any combination of outcomes. And there's many we could cook up. For this example, we could say let A be the event that we roll an even number. So we're going to be able to get a 2, a 4, or a 6 on rolling a single die. And a probability is going to be a ratio of the size, or what we call the cardinality, of the event divided by the size or the cardinality of the entire sample space. So since there's 3 outcomes or items inside of event A, and there's 6 outcomes or items inside of the sample space, we would go 3 divided by 6, which is going to give us about half, or 0.50. It is important to know when we're talking about probabilities, we talk more about theoretical probability, which is the law of large numbers. So if we toss a dice 6 times, we're not going to probably get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. That's the long-term outcome. If we start tossing it enough times, we're going to get about a 1, 1/6 of the time, a 2, 1/6 of the time. But that only happens on the long term. If I roll it 6 times, it's possible I could, not even roll a 2 or not even get a 5. So think of the law of large numbers. We're talking about theoretical probabilities. What we actually end up rolling, or what we observe, is what we talk about empirical probability. And so let's talk about OR here, about some events here. And so now we're going to be talking about 2 events. So one event here, let's let A that we get an even number. And then B is going to be a different event that we get a number that's 4 or smaller. And so we want to find a probability that we get A or B. And when we talk about OR, we're talking about the union of these. You've probably seen a notation as in with the U symbol, so a union here. So what we're saying is, as long as one of those outcomes is in one of the sets, it's going to go ahead and be in the collection of the OR. So 2, 4, and 6 are inside of our set. And then also for B, we have 1, 2, 3, 4. Now notice I don't have to list 2 twice or 4 twice. Once you get it once, it ends up being in the set there. So union is going to be kind of just everything, but you don't need to double list stuff. We could also talk about an AND of events here. So probability of A and B. And we'll call this an intersection, kind of like an upside down U here. And here, as we want the outcomes to be in both of them, it has to be in A and in B. So as we're looking at these here, the only ones that are actually in both are going to be 2 and 4. So if it's AND, it has to be in both of those. So A and B is going to be the set of 2 and 4. We also have this idea of the complement. And the complement is kind of the opposite of, or what's not inside of our set. So, or not inside our event. So if we're talking about, again, a single die, we have the values 1 through 6 in our sample space. If I want to roll an even number, that's 2, 4, and 6. So A prime, which is a complement, would be that I don't roll an even number, that I don't get a 2, 4, and 6. So what's left over? It would be all the odds, a 1, a 3, and a 5. And complements, again, together, they should add up to the entire sample space. They should account for 100%. And then conditional probability, we're looking at 2 events, but we're saying that one of these events already occurred. So we read this as a probability of A given B, and that's equal to the probability of A and B divided by the probability of B. Okay, so let's go ahead and use these values that we have here. So we want the probability of A, that we actually get a 2, 4, or 6, but we're giving the hint that we already rolled a 1, 2, 3, or 4, that B already occurred there. So probability of A and B, we have 2 elements inside of there. So that's where we're getting that 2 over 6 there. And then probability of B, here we have these 4 guys here. That's where that's coming, that 4 out of 6. That's going to give us a half there. Okay, so again, if we are given that B occurred, we can reduce the sample space. Okay. So just to kind of work this out again a bit more intuitively, probability of A given B, I'm giving you the fact that B occurred, so I only have those 4 values to choose from, so that's going to go there in the denominator. And now we want A to occur, and so since 6 is not even in the set of B, that's not even a possible outcome. The only ones that are left over to occur would be 2 and 4 from those that are also in the set of B. So there's only 2 more out of the 4, and that's going to also give us a half there. So we don't have to completely rely on the formula. We'll kind of pull away from it as well and try to do these a bit more intuitively. And so let's look at this example here. So suppose that we have some cards here, and we're going to randomly draw one of these here. And so let's go ahead and let's first list the sample space here, okay? And we're also going to want to do some probabilities. Okay, so we'll look at all of these here. If you want to pause the video and give these a go, and then I'll go ahead and get involved. Okay, so the sample space here is going to be that we have, you could get a green with the number 1, a green with the number 2, or a green with the number 3, because there's 3 green cards here. And then we could also get the yellows, and there are 6 of those. So the sample space would be that you get G1, G2, G3, Y1, Y2, all the way up to Y6. Probability of Y here is going to be, well, there's 6 yellow cards out of the entire sample space, which is 9. So 6 over 9, and that's going to give us about 0.6667 there. Y and E. So now we want and, so they have to be in both of these. So Y is that we get a yellow, and then E is going to be that we get an even. So how many yellow evens are there? Well, there's this one, and this one here. So 3 of those out of the overall 9. And that gives you 0.3333. And now the OR case, so as long as it's in one or the other, so yellow or even, so that means we're going to have all of these yellows here, and then that it's even, so that's going to end up giving us 1 more here. So because it's either or, so green or yellow. So that gives us 7 out of the 9. And then a conditional one, Y, you pull a card that's yellow given, that it is even. So if we're giving you the fact that it's even, that means that one of these cards here was selected. So there's only 4 of those. And out of those, how many are yellow? 3 of those. So 3 out of 4, or 0.75. And then the complement of E, so the probability of the complement. So E is that it is even, so we want that we do not get an even. So since we already, the probability that it's even is going to end up being 4 here out of 9. So the complement would be 1 minus 4 out of 9, because they should add up to the whole entire sample space, that 100% or 1. So we could go ahead and use that formula there and just subtract the difference. Or you could count the ones that are not even, which will be 5 of them. In 4.2, we're going to continue our talk about terminology with independent and mutually exclusive events here. So we say 2 events are independent when the outcome of one doesn't affect the other. And this is going to be the case of with replacement. So if we're selecting students, we pull one of them out, we're going to give them a get out of homework free card. And then we put that person back in. So on the second selection, when I draw a student, it's possible that person could get selected again. So it doesn't really matter who got selected the first time. Everyone's still possible to get selected the second time. So also, we could talk about a dependent, and this is going to be the case without replacement. So the outcome of one does affect the other. So if I'm pulling out a student and then I don't put them back in, now I'm going to go select another one. So on the second selection, there's less students. You're going to have a higher probability of being selected. Independent events, these are some ways to just mathematically check. And so if we look at these conditional ones here, it's a conditional probability, but since independent, it doesn't matter what happened before. The probability of A given B will just be the probability of A, because it's irrelevant what had happened prior to that. So let's start off with our, just to kind of illustrate this. Our original definition of conditional probability, a probability of A given B is the probability of A and B over the probability of B. But because they're independent here, we know the probability of A and B is just going to be the multiplication of those two given from here. And then from that, we could create a factor of 1, and we're just going to get our probability of A in this case. Mutually exclusive, meaning that they cannot occur at the same time. And here's another mathematical way to just kind of check that. The probability of A and B should equal to 0 because they can't occur. They have nothing in common. So let's consider 2 sets here, or 2 events. I have set A, which consists of the first 5 integers, and then B consisting of 6, 7, and 8. Well, here's our an image for A, and inside of there live the items of A, so the numbers 1 through 5. Well, inside of B live the numbers 6, 7, and 8. So notice there is no overlap. There are no numbers that occur in both of these. So we sometimes refer to this as disjoint as well as mutually exclusive. And we'll take a later look at some Venn diagrams in later sections, but just kind of a quick visual here. Let's also look at the case for not mutually exclusive. And so not mutually exclusive, there's going to be an overlap here. So let's create an event A, which is the numbers 1 through 5, or the integers. And then B is going to be even numbers, 2, 4, 6, and 8. So when we draw the numbers of A, all 5 numbers live inside of A here. And when we draw the numbers of B here, 2, 4, 6, and 8 live inside of B. But notice that there is that overlap between them. So this would be a visual representation of things that are not mutually exclusive. So you could actually be in both events at the same time here. And so let's go ahead and look at this example. So if you want to go ahead and pause it here, give it a go, and then I'll go ahead and work it out. So let's look at A here. To show independence, we need to show one of the following here. So any of these three will suffice in order to show independence. Let's just go ahead and pick the first one here. So probability of C given D. And so we'll start off with our general definition here. And we're going to plug in what we know here. So probability of C and D is actually given to us already. So that one is given to us right here. And then we also have the probability of D, which is given to us right here as well. So we're just plugging those in. And we're going to get 0.75, which in fact is the probability of C. So since those two are equal to one another here, then we could say that it is independent. Okay. Let's look at part B here. To show mutually exclusive, we need to show that the probability of C and D is equal to 0. And so this is actually given to us. The probability of C and D is equal to 0.225. So that was given to us, which is not 0. So this guy is not going to be mutually exclusive. So we're looking at it right here. So that was actually given to us. However, let's just say it wasn't given to us. How could we calculate this? Let's use some algebra here. So there's our original definition, which we know 0.75, and probability of D is 0.3. So that's given from us. We're just going to go ahead and plug this in for the conditional probability here. And if we move things around here, multiply both sides by the denominator, we're going to get the probability of C and D is equal to 0.75 times 0.3 here, which in fact is not equal to 0. So there's another way to just use the formulas in order to show that. Let's try this last one here. What is the conditional probability? Right, so if we're looking at the intersection of two sets, right, it doesn't matter which order we actually put them in. So when we talk about the AND case here, we're looking at that middle portion. So probability of D and C is really the same as the probability of C and D. So for AND, it's cumulative. We could swap the order of those and it won't make a difference because we're just pulling items. So plugging this in to our formula here, we're going to get 0.225 over 0.75. So we're just plugging those in and we get 0.3. We could have also shown, since C and D are independent, then we could have used one of the reduced formulas here, specifically this one. And so probability of D given C is equal to the probability of D, which is 0.3. So nice little shortcut if we're using some of the formulas.